going to look at the hydrolysis that gives rise to what makes a solution acidic in this case. What we have is a 10th molar solution of nickel 2 sulfate, and we find if we measure the pH of this solution that the pH is 3.04. What this means is that the cation is involved in some kind of hydrolysis equilibrium that makes the solution acidic. Now what we're going to do is we're going to write a simplified version of this equilibrium for the purposes of this video. It's a little bit more complicated than this, but essentially what it is it's a Lewis acid base interaction between the cation and a water molecule. So since the pH is low, we know that the cation is what's involved in the hydrolysis equilibrium, or what is dominating the hydrolysis equilibria that take place in this solution. So in this case, our cation is nickel 2. So what happens is the nickel 2 is a Lewis acid, and it acts as a Lewis acid toward a water molecule. So instead of abstracting a proton as a base would, what it does is essentially abstracts hydroxide ion from the water molecule, forming this complex ion, where we have one hydroxide ion bound to nickel 2 ion. And the result is we also have hydrogen ion in solution. Now if we were to write a Ka for this, the Ka is going to look like this. It's going to be the concentration of the hydrogen ion times the concentration of this complex divided by the concentration of nickel 2 ion in solution to begin with. Now, since we do have a measured pH, we can calculate the concentration of the hydrogen ion, and that's what we're going to do next. Concentration of hydrogen ion is equal to 10 raised to the negative pH molar. So in this case, 10 raised to the negative 3.08 molar. Which gives us 9.1 times 10 to the negative 4th molar. Now, since this is a hydrolysis equilibrium and both products come from the same source, what we can say is that the concentration of the nickel hydroxyl complex is the same as that of the hydrogen ion. Since both of them come from the same place. Now, for the purposes of solving our Ka, the only thing we have to figure out at this point is what is the concentration of the nickel 2 ion. And what we can say is that the concentration of nickel 2 ion is the remainder, what has not hydrolyzed. So in this case, what we're going to do is we're simply going to subtract the concentration of the hydrolyzed portion from the original concentration. So we have the original concentration of nickel 2 is going to be 0.0 or 0.10 molar, and we're going to subtract from that 9.1 times 10 to the negative 4th molar. If you do this subtraction and round back to the appropriate number of significant figures, it doesn't change the molarity of the nickel 2. An important reminder for you, though, is that when you do this, you should never assume that the concentration of the hydrolyzed species is insignificant with respect to the concentration of the non-hydrolyzed species. You should always do this subtraction. Most of the time you're going to end up rounding back to the original molarity, but there are rare instances where you don't, and there's at least one instance where this is true in the lab that you're going to be doing. So the next thing we have to do then is simply calculate the Ka for this. So all we do is plug the numbers in. Since both concentrations on the top are the same, all I have to do is take 9.1 times 10 to the negative 4th and square it, and then divide that by 0.10. The result is 8.3 times 10 to the negative sixth. And that's the Ka that we would report for this particular hydrolysis equilibrium.